Hey guys, this is going to be a fairly quick video for 15.6 through 15.12. The first thing that we need to talk about, we talked about heat engines last time we met, and talked about the efficiency of heat engine, things along those lines. Today we're going to talk about air conditioning systems or refrigeration systems, which are essentially the same thing. It's about how do you get something, a place that is cool, okay, or cooler than outside, to force heat out of an environment. Okay, you think about it, heat wants to flow from high temperature or high heat energy to low energy heat. So we want to go, basically we want to see temperature always wants to go towards the cooler temperature to level out. But that's not going to be what we want in terms of refrigeration. Even though the temperature might be quite low in a refrigeration system or inside your home, you might have it down to 68 degrees during the summer, nice and cool as compared to 90 degrees outside. Well, the heat from outside is going to try, and it's going to effectively infiltrate your home. Even through the insulation and everything, it's going to find ways into your home. Through convection and radiation and conduction, it's going to find its way into your home. So for us to take the heat that is in your home, and that's going to continue to come into your home, and force it out of your house into a higher heat state, we're going to be defying the first law of thermodynamics, or second law of thermodynamics, sorry. The heat wants to flow from high heat to low heat and level them off. So for us to force heat out of this low heat section or area, we're going to have to do some work. Okay, it's not going to happen naturally. But if we do work through condensing and expanding fluids, okay, or different materials that will absorb some of that heat, and then we can evacuate it out the outside, that can be something, a way in which we're able to do that. But we're going to have to do some work. So just real quick, QH is still going to equal QL plus the work that we're doing. So the energy still adds up, still all equals. You can see these two things are being added together, and so we get that from there. Now, the more work we have to do, the less efficient something is. But we're not going to measure the efficiency the same way we would with a heat engine. Instead, we have something called the coefficient of performance, or COP. And that is, how much work do you have to do relative to the temperature that you're going to try and reduce to. And if we look at, let me grab my formula sheet. Should have had it ready. But if we look at our formula sheet for the COP, our coefficient of performance is calculated by, where do we go? COP. Wrong one. Here we go. The COP for refrigeration is QL over W. What is the heat in the cool system, and how much work are you doing to keep it there, keep it down? Okay, so we're going to have to do a certain amount of work to pull some heat out of that QL. And that's going to give us a coefficient of performance. Obviously, if we don't have to do very much work, if work goes down, then the overall result of this fraction is a rise. So that means that the less work we have to do, the higher our coefficient of performance is. Now there is a situation like the Carnot engine where we can talk about the ideal perfect situation. And that will be based on temperatures in Kelvin. Okay? And when we do that, okay, what we find is that we have TL divided by TH minus TL. And so, we can't divide by 0, but we can think about something very close to that. If we ever got the temperature of the inside and outside to match, right? If we got the inside of the refrigerator to be the same as the temperature on the outside, this denominator would essentially be 0. If it was 0, okay, we think about dividing by 0, we get those asymptotes in mathematics. That would tell me that the COP would be approaching infinity. meaning we'd have a perfectly efficient, perfect refrigeration system. Well, that's because you'd unplug it. If the temperature on the inside and outside are the same, you don't need to run the refrigeration. Think about putting your refrigerator outside during the winter. Do you really need to keep the refrigerator door closed? Well, the answer is no, because it's going to be the same temperature. It might be even colder outside than it is inside. And so why not let the natural air do it? Well, we want to control that temperature to a specific setting. We don't want to let it fluctuate with the temperature. Plus, what happens when you have the sunshine on it? It's going to warm it up. So there's obviously a reason for refrigeration, but this idea that mathematically, the closer we get the temperatures, the more efficient our refrigeration will be. So it's kind of a neat little deal in doing that. There is one other topic that we need to talk about, and I, don't want to get too deep into it because we're doing a basic level of physics, but this concept of entropy. Entropy is a measurement of the state of a system, just like a system will have a certain pressure, a certain volume, a certain temperature. Entropy is a measurement of the stability of a system, and we know that over time, entropy will increase. You can think of entropy as a way to measure the amount of disorder or organization in a system. If something is going from in its natural state, things will move naturally from organized to disorganized, never in reverse. And so an example of this would be if you drop like something glass, maybe a glass cup or a plate on the ground, it will shatter and become disorganized. You would never expect it to do it in reverse. You would never expect that plate to bounce off the floor from shards and suddenly reassemble into a perfectly organized plate. Similarly, the atoms and the molecules that each of us are composed of over time become disassociated with each other. Think about it this way. In 1,000 years, if I dig up a body that's totally decayed and rotted, am I going to be able to tell which atoms and molecules came from the person's eye versus what came from their fingertips? The answer is no. It's going to disassociate to the point when most of the matter won't even be there anymore. It will have been turned into dirt and eaten and all those other things that happen. The body would just be different. We wouldn't be able to keep track of all of the individual components. Very disorganized at that point. And so we know that over time things are going to become more disorganized. So one of the ways we can talk about that is the nature of our different phases. If you think about a solid structure, it's very organized. That means that we would have low entropy. But as we go to a more disorganized state, like a liquid, or even more to a gas, gases are very disorganized. They're flowing around doing whatever business they can, going whichever way they can. That would be an example where the entropy is much higher. So it's a way to measure like the chaotic nature of the material. And if you see something in nature going from a solid state to a gas, like dry ice, we know that it's having an increase in entropy. If we ever want to know how much increase in entropy something had, we have this equation, delta S, so the change in entropy is equal to the heat change divided by the temperature at which that heat changes. So this is in Kelvin, of course, and Q is a measurement in joules. So entropy is measured in joules per Kelvin. This Q could be one of two types. We can talk about mL because we have a phase change like we're talking about. We can also talk about MC delta T. Now again, I said that typically in a natural setting, entropy wants to increase. And entropy will increase over time. But you might be able to find a situation when, for instance, liquid water freezes naturally. And so you would say, look, we just lost entropy here. But the guarantee is, as that heat left the water, it went somewhere else. And elsewhere there would have been an equal increase in entropy. So we're never going to see a true decrease in entropy because it's always increasing somewhere else because of the losses in that system. But individual systems can increase and decrease in entropy in terms of their organization. Pretty easy calculation for you to make. Shouldn't be too much there. Good luck, guys. We'll see you when we see you.